Good morning, everyone. It's my great pleasure to attend this great conference on circular economy. My name is Simin Yu. I'm a lecturer at the University of Glasgow. And today I'm going to briefly introduce some of our preliminary research about comparing the global warming potentials of different waste to hydrogen technologies. So sustainable waste management is one of the global challenges that call for effective or efficient actions, and is not only immediately affecting the quality of our daily life, it also has a significance to achieving sustainable development, sustainable society in the long term. In particular, waste management plays a non-trivial role in mitigating climate change. And on the other hand, the hydrogen development has been considered to be effective measures for mitigating the climate change, for achieving sustainable development in the long term. So in this work, we're gonna consider about comparing the global warming potentials of different waste to hydrogen technologies based on the life cycle assessment method. As a side note, hydrogen development is also receiving increasing attention in the UK. For example, the UK is planning to develop one of their first hydrogen power trains around the world in the coming few years. So it will be interesting to explore if it's environmentally favorable to consider the waste as a source of hydrogen in addition to those existing methods, for example, based on the fossil fuels or the ones from the water electrolysis. This slide shows the general waste management hierarchy. So definitely for the waste, it should be considered to be recycled, reused, or reduced, which sits in at the top of this waste management hierarchy. Unfortunately, not all the waste could be handled by those three prioritized methods. And for those non-recyclable ones, alternative methods need to be found to achieve sustainable management. Conventionally, landfill and incineration have been considered as an effective method to handle those non-recyclable ones. And during the past decades, some relatively advanced technologies such as gasification, pyrolysis, anaerobic digestion, and fermentation have receiving increasing attention due to their potential to be more efficient, to be more clean. So in this analysis, we will consider two technologies. One is the gasification, as highlight in purple in the graph. Another is fermentation. For the gasification technology, we consider it used to handle the waste wood and the municipal solid waste as an overall type of a feedstock. The reason why we consider a gasification here is because, first of all, it's proved to be effective to recover hydrogen from those mentioned feedstock. Secondly, the technology readiness of this process is relatively high, which means that once it's found to be environmental friendly, it's possible that some scaling up research study deployment even could be implemented. The third reason is that there are relatively abundant data about this technology, which will facilitate our preliminary analysis. But of course, we are aware of that for this technology, there are different stages and different operation factors, equipment conditions will affect the energy efficiency, affect the overall performance of this technology. And there are a variety of data sets about this. But for our analysis, we will consider some average data we got from the literature. The second technology is fermentation, which is the one that could convert the organic waste into hydrogen. And we consider to use this technology to handle wet waste, specifically food waste and sludge. And we also consider the potential requirement of this technology about pretreatment. And this pretreatment stage will definitely affect the overall global warming potential of the system considered. In addition to the duct fermentation, we considered we also explore the potential to have a integrated development that is based on the combination of a duct fermentation and a photo fermentation. So the reason why to have this consideration is that to try to do some initial exploration about having this kind of integrated design, hybrid design to enhance the resource utilization. And before we carry out their analysis, we also try to identify the potential issues or limitations of these two type of technologies, which will potentially help us to shape their or design and the configurations of the systems or improve their overall performances of their technology or system we considered in the analysis. For example, we are aware of that for solid waste, it's typically featured by no energy intensity with potential impurities and high moisture content of solid waste might be a potential concern to the thermochemical process, that is a gasification technology. Well, for the food waste treatment, the ratio of carbohydrates to lipids and to proteins will potentially affect the overall performance and energy efficiency of the technology. And for the gasification technology, which generates syngas as a direct product, a subsequent syngas upgrading process needed, which will incur additional energy and emissions. So this is the system boundary of our assessment. We consider the 4 main stages ranging from sorting, main process to syngas cleaning for gasification and the storage of hydrogen for subsequent or downstream application. And we also consider that those considered technologies, we evaluated will generate hydrogen with purity higher than 99%. And our initial analysis adopted a functional unit to be 1 ton of waste feedstock. So let's see some results. So this slide shows the comparison of the global warming potential of those 4 technologies or configurations we considered, which are duct fermentation, and duct and photo fermentation, and municipal solid waste gasification, and the waste oil gasification. We found actually the waste oil gasification has the highest global warming potential, and generally the gasification technologies will have higher global warming potentials than the fermentation technologies in terms of 1 ton of feedstock treated. This is because for these 2 technologies, gasification-based technologies, we consider the hydrogen upgrading processes involving, for example, cleaning, scrubbing, hydrogen separation, as well as storage and compression. So those stages will contribute significantly um, um, to the global warming potential. And when we compare the waste wood with municipal solid waste, we found waste wood has a higher global warming potential than the municipal solid waste based on 1 ton of input. In this graph, we try to compare our analysis result with those reported from the existing literatures. We also compare the global warming potential of the technologies we of our considered by our study with that of steam methane reforming um, technology, which is the conventional one that generate hydrogen from the fossil fuels. And the results is generally there's some differences between the results of ours and that reported by the existing studies. And we are in the stage about exploring the potential reasons behind these differences. There are some possible reasons include a different system boundary consideration, different process, parameters, applications, and so on. So this highlights the importance to have a standardized or consistent system boundary or consideration in this kind of research for non-term or future co-study comparisons. And I also find very interesting that the global warming potential generally increases as yields of hydrogen. So the SMR generally has the highest yields for hydrogen. It's also corresponded to the highest global warming potential. And we will explore this a little bit more at the following slides. So this slide is basically try to explore the relationship between the global warming potential and the yields of hydrogen. So in this case, we consider the functional unit to be 1 kilogram of hydrogen produced instead of 1 ton of feedstock treated. So in this case, very interestingly, we found that waste gasification has the lowest global warming potential. Well, in our very first graph, we found the waste gasification has highest global warming potential in terms of 1 ton of feedstock treated. This means that the functional unit selection is important for get a comparison, for decide the comparative relationship between these two different technologies. But definitely the selection of the functional unit will depend on the demands of the development in many cases. And in this case, the fermentation technologies will have the high global potentials compared to the gasification-based technologies. This is because the gasification-based technologies generally has higher hydrogen yields. And we're also doing cost-benefit analysis and sensitivity analysis, try to explore the association between the life cycle assessment results and the economic feasibility or profitability of these different types of technologies. So in conclusion, our preliminary research found that actually waste to hydrogen technology is important if we want to have no carbon hydrogen production as compared to the existing fossil fuels based technologies. And specifically, we find that the biogas gasification has a global warming potential around 1/25 of SMR, while MSW global warming potential, its global warming potential is around 1/23 of SMR. And there are additional factors we need to consider in order to improve our analysis, also improve the design of our configurations. And we are currently working on that. And hopefully we will be able to communicate about that in the future. conferences. So thank you so much, and hopefully enjoyed it, and looking forward to meet you in person in the future.